Here in section 4.5, we're going to talk about the derivatives of logarithmic functions. Specifically, we're just going to learn about the derivative of the natural log function. So there are two rules to this section. One of them is the basic rule of the general, just plain old natural log of x. And the second one is how we can extend that using the chain rule. Okay, so the first derivative rule is how we differentiate the derivative of the natural log of x. Okay, so this is pretty much our last derivative rule, the last kind of function that we're going to learn how to differentiate. Okay, so the derivative of d dx of the natural log of just x, simple plain old natural log of x. The derivative, I say that word so much that it just comes out really weird sometimes. The derivative of the natural log of just x ends up being, there's no natural log in it, there's no e, it ends up actually being a power of x. And the power of x that it ends up being is to the negative 1, or 1 over x. So that's it. The natural log goes away when you differentiate, and you just get 1 over x. Now, before we apply the chain rule to this, here is just a really quick graphical little explanation for the derivative of the natural log of x being 1 over x. If we look at the function, the natural log of x, we reviewed in the natural log review section that the graph of this thing looks like this. Now, this function, as we saw, is always increasing. It's always going up as you go from left to right. If you graph the derivative, 1 over x, it does have two parts to it. It goes down like this, and then it goes down like that. That's got a vertical asymptote at x equals 0. But since the natural log function only has domain positive x values, then if we only need basically this part of that graph for 1 over x. And we can see that the graph of this function for positive x values is always positive. And if we remember that the function increasing means a positive derivative, then this is one reason why that makes sense. The tangent line is really steep over in this direction or in this side, and so we have the derivative. It's really high. And as we get closer to x equals 0, this original natural log graph gets very, very steep, and the derivative function goes very, very high up. In the other direction, as you look at the natural log of x going out this way, it starts to get less and less and less steep. And so we can see that in the graph of the derivative function, it's approaching 0. So applying this with the chain rule, the second rule is how to differentiate the natural log of a function of x. Okay, so the derivative of the natural log of a function of x, so maybe it's x squared or 3x to the 4th plus 1 or something like that. Square root of x, if we want to find the natural log of something more than just x inside, here's how we do that with the chain rule. Now I'm going to use u for the inside function. Okay, we differentiate the outside, so we will get the derivative of the natural log function, which is 1 over whatever is inside. But then with the chain rule, what we have to do is multiply this by the derivative of the inside, and that's u prime. Okay, so it's 1 over u times u prime, 1 over the inside times the derivative of the inside. Another way that we can just simplify this right off the bat is saying that it's the derivative of the inside over the inside. So u prime over u. Another way that we can notate this, if you don't like, like u, although I will use this, is you can say the derivative of the natural log of a function of x. We can write like just f of x. Okay, it'll be 1 over f of x, 1 over the function of x inside, and then multiplied by the derivative of the inside, so times f prime of x. And we can still rewrite that and all in one go kind of try to simplify, and we can put that as f prime of x over f of x. Okay, so here's a little mathematical proof as to why this is what it is. So, why is the derivative of the natural log of x 1 over x? You don't have to know how to do this, but you should be able to follow along. So if y is equal to the natural log of x, then, we're trying to prove the derivative rule of this. So we have to use what we know. So if y is the natural log of x, then we can write this as x equals e to the y. Now, x equals e to the y is nice because we know how to differentiate e to something. But the problem is that this isn't solved for y. So we're going to need to differentiate this implicitly. Okay, so if we differentiate x, we just get 1. And if we differentiate e to the y on this side, on the right-hand side here, we get itself. So we'll get e to the y. But then remember, we have to multiply by the derivative of the exponent. The derivative of y is 1, but this is implicit, so we have to multiply this by dy dx. Now, if we solve this for dy dx, which is what we're looking for, we'll just divide by e to the y. So 1 over e to the y does not look like x. However, if you look up here, e to the y is actually equal to x because of, what we started with, y equals the natural log of x. So if we just substitute back in, x equals e to the y, we get 1 over x equals dy dx. So here's like a neat little math proof. As you get into like higher math classes, you would spend more time on math proofs instead of computing things. So when we're done proving something, we put a little box here, and we fill it in if you want, and it just means like we showed what we wanted to show. So here's a little math proof. And here's just something else that is kind of neat about the derivatives of things. If you think about all of the powers of x that we've learned to differentiate, right, x cubed becomes 3x squared, x to the second loses a degree and becomes 2x to the first, x to the first loses a degree and becomes x to the 0, x to the 0 loses a degree, that's just 1, so that becomes 0. And then x to the negative 1 loses a degree and becomes negative 2. X to the negative 2 loses a degree. Oops, and that should be x to the negative 3 there. So we actually have a gap where in our derivative column, in here, we don't have x to the negative 1. It skips. We have this gap. And so the natural log of x kind of fills in this gap, which is kind of nice. So it's the only function. It's the only function where you get, like a power of x as your derivative when you didn't start with a power of x, which is kind of cool. So this natural log of x here fills in the gap. Okay, so let's practice using this and differentiating some things involving the natural log of x. Okay, so let's start with the natural log of 2x. So of course that is not just the natural log of x, so we have to use our rule with the chain rule. So let's say u equals 2x, and u prime, the derivative of that is equal to 2. It's been a while since my iPad acted up like this. Come on, you can do it. Okay, so the derivative of the natural log of 2x, we've got u equals 2x and u prime equals 2. So if we're going to find the derivative of the entire function y prime, then we'll just have u prime over u. So that's 2 over 2x. And we can simplify this. The 2's can cancel, and we just get 1 over x. There's the derivative of the natural log of 2x. The natural log of x to the third, we are going to want to use the chain rule again. So we don't have just x inside of the natural log. So we can find out what our u is. So that's, of course, x to the third. Okay, u prime, the derivative of that, that'll be 3x to the second. And so when we differentiate the whole thing here, y prime, we'll get u prime over u. So that'll be 3x squared over x to the third. Now, if we simplify this, which we can do in some cases, we can just cancel out some x's here. So up top, we'll just have 3, and in the bottom, we've got an extra x. So we'll have 3 over x as our derivative of the natural log of x cubed. All right, example number 3, we've got y equals the natural log whole thing to the third power. Now, this function is, well, overall, the bigger picture of it is something to the third power. And the something that's raised to the third is not just x. So in this case, we have to use first the general power rule. So what that is going to say is that we're going to take this 3 down and multiply in the front. Now, this is not the log law number 3 with exponents. This 3 is not inside of the x to the third. So in example 2, what we could have done is bring this 3 down in the front and bring this 3 down in the front and multiply and get 3 natural log of x. Okay, so optionally for here, what we could have done is say y equals 3 natural log of just x. Then when we find the derivative, that would be 3 times the derivative of the natural log of x, which is 1 over x. And so simplifying that gives us 3 over x. But here this exponent is not on the x inside of here, it's on the entire thing. So we need the general power rule. Okay, so what that says is that we will take the 3 down in the front and multiply. We leave the inside, the base, the same. Then we subtract 1 from the exponent, so we'll get 3 natural log of x squared. Right, that's the derivative of something cubed. But then, since the inside is not just x, we've got to go in and multiply by the derivative of the natural log of x, which is our new piece here. So that's 1 over x. Okay, so general power rule, bring the 3 down and multiply in the front. Then we've got the inside the same, subtract 1 from here. And then this is the derivative of the inside. Simplifying this, it's just nice if we can write it in one fraction. So we could just multiply across the top and multiply across the bottom, and then we'll get 3 natural log of x squared all over x. Example number 4, we've got y equals natural log of a long polynomial, 3x to the fourth minus 2x cubed plus 4x squared minus 5x. Okay, now remember log law, this is not multiply, so we can't just distribute the natural log into these 4 things. Maybe if we wanted to, we could expand this, but I don't know. It doesn't look like there's a product. Factoring a 4th degree thing isn't easy. So I would just straight off the bat just say, all right, well, hey, we've got u, right? That's all of this stuff. And to differentiate this, we'll do u prime over u. So here's u prime. The derivative of this, we'll have 12x to the third. minus 6x squared plus 8x minus 5. Okay, to find the derivative of the entire thing, we'll just put u prime over u, and that's it. Natural log's derivative, u prime over u. So we'll do 12x to the third minus 6x squared plus 8x minus 5. And then that's all over 3x to the fourth minus 2x to the third plus 4x squared minus 5x. Don't even, simplifying this, I don't even know, maybe we could factor this, but no need at all. We can just leave it exactly like that. All right, example number 5, we've got the natural log of the square root of x, and that's all over x. Okay, so here we will definitely need the quotient rule. We've got some stuff with x up top, and we've got some stuff with x in the bottom. Now to differentiate, just thinking ahead a little bit, well, I guess so we have a numerator and a denominator when we are using the quotient rule, right? So we've got n and we've got d. Now d prime is easy, right? That's just 1. But to find the derivative of n, or the numerator, think about what it would mean to differentiate natural log of the square root of x. We would get 1 over the square root of x, then we'd have to multiply by the derivative of the square root of x. That's not too bad, but it's a little more complicated than it needs to be, because what we could say is we could write this differently using our log laws, right? So this radical x is the same as x to the 1/2. So let's just rewrite this as 1/2 x, 1/2 natural log of x all divided by x. That's a little bit better, and we can even say that this is the natural log of x. We can bring that 2 down into the denominator and make that natural log of x over 2x. Okay, so now we've got an n where the n prime is pretty simple, right? Natural log of x's derivative, that's the new stuff. So that's 1 over x. And now our d prime will be 2. So I think this is a little bit easier to use the quotient rule on. Maybe I should have written this up here, right? Quotient rule. So let's go ahead and put that together. So y prime now, the derivative of the entire thing will be the bottom 2x times the derivative of the top, 1 over x, minus the top natural log of x times the derivative of the bottom, which is 2. And that's all over the bottom squared. Okay, now to simplify this, we've got here 2x essentially divided by x, so we can cancel these x's. And that'll just leave us with 2. Then we've got minus, which is better if we write this as 2 natural log of x. And then when we square the 2x in the bottom, we have to square the 2 to get 4, and then also the x to get x squared. And the only last thing we could do here is factor out a 2 from the top. Or we could cancel these 2's here and get 1's. If we can cancel a 2 everywhere, then that's okay. So we can write this as 1 minus the natural log of x all over 2x to the second. And there's our derivative. Okay, so we can use all of the rules that we know so far. It's just that now we have a new function that we can throw into the mix. All right, example number 6 is y equals x to the third times the natural log of x. Now here we need the product rule. And I don't think there's anything really to do here with simplifying the natural log or anything, because it already has, it's already just x in here. So when that's the case, that's the best case scenario, simplify things inside of the natural log. So let's just get started using our product rule formula. All right, so we will have, well, let's see, we have u and v. So let's let u equal x to the third. So then u prime will be 3x squared. Okay, v will be the natural log of x. So here's the new stuff, v prime will be 1 over x. So let's put this together using the product rule. So it's first times the derivative of the second. So u times v prime. So that's x to the third times 1 over x. And then we add the second natural log of x times the derivative of the first, which is 3x to the second. Simplifying this, we've got x to the third basically over x, so we can cancel one of those. We'll just get x to the second. And then normally we just write the simple powers of x in front of natural log so that we don't confuse what's inside of the natural log and what isn't. So I would just rewrite that second piece as 3x squared times the natural log of x. And there's our derivative. And we could simplify this by factoring out a GCF, but this is good.